Hello. Happy Friday. Hey Thud Turtle. Is there a specific way the Matlab code should be placed into the assignment write-up, such as a screenshot, copy and paste, or attach a PDF to the end? You know, any of those ways would be acceptable to me, as long as it's there. Oh yeah, the Matlab publish is a really good one, and then just attach that to your assignment. Makes a nice PDF. You're very welcome. Is the assignment going all right? Did you start it? Happy Friday to everybody. Finishing it up right now. Don't want to do any homework during the weekend. Good for you. It's always great if you can break contact with school at least a little bit over the weekend. I know it's tough. So many assignments and stuff. But if you can do it, that's awesome. The assignment wasn't that bad, says Bobby. With the extension, I thought it was going to be much worse than it was. No, yeah. Yeah, once you get into it, not too bad. Not too bad at all. Okay, how about we get started here? We're going to talk about Lab 3, which is our very last lab, and then you're going to be done with lab reports. So after that, we just have one workshop, one more assignment. You guys are in the home stretch, so good stuff. So I kind of have this set of notes here with some blanks that I'm going to use to go through the stuff for today. So don't worry about following along with everything that I write, because there might be more written here than you can keep up with in real time. I just want to show you the main concepts that we're dealing with for this lab. So it's very related to assignment number 2. So it's gonna feel very, very similar. Let's turn the music a little bit more. So we're gonna be using frequency response techniques to get a model, which is, it's gonna be a transfer function for a flexible beam. And I'll show you what it looks like in just a second. I have a little picture of what we're going to use in the lab. But I thought I might bring in some motivation first. Like, why model a flexible beam? Like, think of it like a metal ruler, kind of. I'll just show you really quick what it is. Yeah, it's basically this thin metal rod. And what's my favorite element of aviation? What's the best to study? I love control systems. So why are we modeling a flexible beam? So just like a couple places where you're going to see stuff like this. I mean, obviously a helicopter blade is not as compliant as what you're going to see in this lab. But helicopter blades do vibrate as they turn. And you have to model that and study it and be able to counteract the vibrations as it rotates. If you think of a satellite up in space with these long panels, there was a lot of research in aerospace engineering in the 90s that was focused on vibration suppression of structural components. So like you guys know Professor Mook, like he did research on structural vibrations in space. And so the principles come here. I've heard blades, if they don't spin fast enough, they'll actually bend if they spin too slow. Yeah, there's the centrifugal forces in there that are important. In space, a speck of dust will punch a hole into anything. A lot of speed. Isn't that the like, what was that movie with, oh, what's her name? But have you seen the film Gravity? Isn't it like a little speck like destroys their space station? Also, like, I'll just bring up one more example here. Fast robotic manipulators. I want to take vibration and shock, but it sounds tough. Vibration and shock is going to cover a lot of this too. So Mostafa No teaches that, right? Like, do you know about his research? He, like, I'm not the best person to explain it. I don't want to destroy it, but my understanding is he builds these structures that are called meta materials, and they're kind of like alternating, like, think of a bar, but it's made up of these like alternating materials. And I don't know what materials he uses, but each of these has specific like vibration properties. And then if you apply some force on one end, if it's at a specific frequency, I believe that the vibration at the other end is just nothing. So for certain frequencies, this thing, you have to ask him about it. He would explain it much better. But that's my understanding. There's a what's called like a dead band in here, where frequencies of excitation within that bandwidth result in like no vibration on the other side. It's like if you tie a ball to a string and start swinging it. Oh yeah, I see ZHB was asking some questions. I can come back to that at the end of class. Oh yeah, but I was going to say fast robotic manipulators. So a robotic manipulator, typically we're talking about a robot with a couple links here. So maybe it's mounted to something. But as we make these robots faster, we also tend to make them out of lighter and less bulky components for these linkages. And a side effect of that is when you have a lighter structure and you're moving it very quickly, you introduce vibrations into the motion. So this is becoming a more and more important part of even modeling different types of manipulators for robotics. You got to remind me at the end of class, there's like a pancake robot, pancake sorting robot or something like that. That's really fun to watch. So remind me about that at the end, and that's a good example. So we're gonna model a flexible beam, and it looks like this. Okay, so this is the way it works. We have a servo motor over here. And so you can see some gears here, but basically this is going to rotate back and forth. And as this rotates, this flexible beam is gonna bend and it's gonna vibrate back and forth. And at the base of the beam, maybe if I zoom in here, actually I think it's on the other side of the beam, but there's a strain gauge here. And so that's going to deform as the beam bends. And that's how we're going to have a calibration quantity related to the deflection of the beam. Okay, so here we go. We're looking for, when we model this thing, we're going to look for a single input, single output model. So let me explain that a little bit more. Our input to the system is the angular displacement of the servo motor. Because the beam is fixed to the servo motor, so as you rotate it back and forth, it's going to affect the beam. And I'm just going to call this angle that it makes theta. All right, and our output is going to be the lateral deflection at the tip of the flexible beam. Oh my goodness, I spelled it B-E-E-M. And we'll call that delta. And I'm going to show you a video of this thing in motion. And actually, how about I show you right now? Let me pull up a video. Where are you? Okay, here we go. Here we go. Let's go over here really quick. I think I want this. So this kind of shows it in slow motion. So the servo motor back here, rotating a little bit back and forth, you can see that. And then the beam is reacting to that. It vibrates. And this is actually at the natural frequency of the beam. So at the natural frequency, very little displacement at the end results in a huge amount of lateral deflection of the beam. And you'll see that in the frequency response. What is the real purpose of that machine? I don't know what you're hinting at. Okay, here we go. I'm going to show you another cool frequency. So this is at a much higher frequency. And what's cool, you can kind of see this. There's a stationary point on here. It's kind of fascinating to watch this. It's all kind of vibrating around this one point. Hello, Not Prof. Good to see you today. Oh, just wondering what it would be used for? No, the only purpose of this apparatus is, let's go back here, is to practice frequency response experiments. So this machine doesn't actually have a practical engineering purpose other than education. So anyways, our input is the angular displacement of the servo motor back here. And then what I mean by the lateral deflection of the beam is like if you drew a straight line like from the base, this is like a projection of where the beam would be if it wasn't bending at all. So the lateral deflection at the tip is if you go to the tip of the beam and draw a perpendicular line from where it would be if it was undeflected, we'll call that delta, the lateral deflection. And it's actually interesting, like you might ask like, well, okay, how do you measure this lateral deflection? I mean, we don't have like a sensor down here at the tip of the beam or something like that. So like I mentioned, there's a strain gauge all the way back here at the base. And what we do prior to running this frequency response experiment is we run a calibration where, let's see, we deflect the beam different values delta. So like we deflect it 1 inch, 2 inches, and we go different directions as well, like 1 inch in the other direction. So like -1 inch, -2 inch. And then what we do is we measure the voltage that's coming off of the strain gauge. And so at each of these test points, you find something like this. And then you can fit it with some line, because the relationship is mostly linear. And then what this allows us to do is when we're running this beam experiment, we're getting voltages from the strain gauge back here. And then for every voltage reading we get, we can relate it back to this equation and say, oh, okay, it's giving us like 0.03 volts. So that means the tip must be deflected 2.5 inches right now. So that's how we measure the deflection at the tip. So we want to find the model that relates theta to delta. And this is what you have to do if you're designing like a vibration suppression control system for like a satellite or for a helicopter blade. You have to have a relationship like this to help you design that control system. So this is something like a calibration equation. Yes, that's exactly it. We have to make a calibration equation relating the tip deflection to the strain gauge voltage so that we can get meaningful results out of this experiment. Okay, so you guys are working on assignment 2 right now. And what I want you to get out of assignment 2 is if you have a linear system, if you give, so let's talk about our flexible beam system. Our input is going to be the servo angle, theta. So what you can do is you can run this at different frequencies. Just have the servo motor pan back and forth and see what the beam does. So this is just a sinusoid. So this is the definition of the amplitude. You guys are familiar with that. But if you feed this through the flexible beam dynamic model, what is the tip deflection going to do? Well, we know that, so let's say this pink line is how the tip of the beam is changing with time. So it's deforming one way and then the other. We know that the frequency of these oscillations is going to be the same as the frequency of the inputs. But you see there's this offset. So that's described by the phase angle. And then the amplitude is actually a little bit different. Well, it could be a lot different at different frequencies. So the way we describe that is we have the original amplitude A times an amplitude ratio. And this is how much the amplitude is well, it's either amplified, like in this case, it looks like what? Maybe the amplitude of the pink signal is 1.5 times the blue signal, so maybe the number in here at this point is like 1.5. So this is what the beam deflection is going to be doing. And what we do in assignment 2 is we test a bunch of different frequencies of inputs, and for each frequency we figure out what that amplitude ratio is and what that phase angle is. So what's important here is that amplitude ratio and the phase angle, they change depending on the input frequency. Like for the DC motor, so what we're doing in assignment 2, if you plot if you have frequency and if you plot the amplitude ratio just goes down, 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 down. Or if you plot it on a logarithmic scale and you do the decibels of the amplitude ratio, it's going to look something like this. So the amplitude ratio changes with frequency. So how do we get a model? You can look at the shape of the frequency response. So like for the DC motor, I'm looking at like this shape. And you know that each unique shape can be fit with a different style of transfer function. So for this shape, I'm going to find a transfer function that behaves in that similar way, and then I'm just going to fine tune the parameters until it fits the data pretty well. So I have an example here, like we're talking about assignment 2. This isn't the solution to assignment 2, it's just an example that I give in the assignment write-up. Say we do like 11 different frequencies and we test. So this top plot is the amplitude ratio. This bottom plot is the phase. So like how much of a delay do we get? A transfer function that fits this really well is a first order transfer function. So specifically, if we have a gain of 5.96 and then we have 1/5 s plus 1, this is what you're seeing for the red line. And you see it matches up with the experimental data reasonably well. You're going to find for the flexible beam, there's a very different shape. I'm trying to remember right now, but it looks like the amplitude ratio, it goes up, and then it comes down, and then it goes like down, and then it goes up again. So it has a very different shape, but it can be fit very nicely by different transfer functions. Okay. So in lab 3, we're going to do the same kind of idea like we're doing in assignment 2. But we're going to use a different approach to get the frequency response of the flexible beam. So let me tell you what I mean. So let's think about the approach that we're using in assignment 2. What is the approach? We have a different test for every frequency. So maybe the first problem is like which frequencies should I test? So like in this example up here, how did I know that if I grab frequencies in this area, like I can grab this feature at the corner and this kind of shape? Like if I tested different frequencies, maybe if I tested higher frequencies, like all of the points over here would be kind of the same, and it wouldn't help me fit this data with the transfer function at all. So a weakness of the approach we use in assignment 2 is the person running the experiment has to have a good idea of which frequencies should be tested. Okay, so that's the first problem. The second problem is you have to run a bunch of tests. Test a bunch of different frequencies. And for each frequency you test, that's another test you have to do. So up in this figure above, we ran 11 tests, and that takes time. And it takes time to analyze each test. And if I want a more accurate depiction, I would have had to run even more tests. So these are the two main weaknesses. Like, you don't know which frequencies you should test in advance. And then even if you have a good idea of the frequency range, you have to run, 10, 20, 50 tests, maybe even more in industry. Okay, so an alternative. What if we could run one test that evaluates a bunch of frequencies at once? Will this note be posted to UB Learns? Yes. Yes, I will. So this would be the dream, right? Like, what if I could just run one test that runs through a bunch of different frequencies and gives me all the information I need? And the beautiful thing is we can do this. It is possible. And that's the technique we're going to show you in Lab 3. Okay. So this alternative, it's rooted in the principle of superposition, which is a cool property of linear systems. So I want to explain to you what superposition is right here. Okay, so let's talk about the flexible beam. So imagine that you give some input U1. So what is U1? It's a sinusoid, and it has an amplitude A1, and the frequency of this sinusoid is omega 1. Well, we know for linear systems what the output is going to look like. So it's going to be, A1 times an amplitude ratio at omega 1. So this notation here, I'm not having the amplitude ratio times omega 1. This is just saying amplitude ratio at omega 1, because the amplitude ratio changes as a function of frequency. Okay, so we're going to have the amplitude change, and then it's going to be multiplied by a sine of the same frequency as the input. So omega 1 is the frequency of the input, so we're going to have omega 1 here, but we're going to have a phase shift, and I'll call this the phase at omega 1. Because remember, the phase changes with frequency. Okay, so one input gives us this output. Okay, so for the sake of this example, assume that there's another input, U2. And it's just a different sinusoid at a different frequency with a different amplitude. So let's just write this out. It'll be the amplitude of that input, and then it's going to be the amplitude ratio, but now it's going to be the amplitude ratio at this frequency, omega 2, which is different than omega 1. So this amplitude ratio is different. This will be a sinusoid with the same frequency as the input, which is omega 2. and the phase difference is going to change. It's going to be whatever the phase angle is at omega 2, because we know phase and amplitude change with frequency. Okay, this is where superposition comes in. All right, we know what the output is going to be if you apply these inputs individually. Like U1 by itself produces Y1. U2 by itself produces Y2. So superposition tells us that if we apply an input that is the addition of two different sinusoidal inputs, or really, I don't even have to say sinusoidal here. It could be any two inputs. The output for this combined input, it's just going to be the addition of the two outputs that we got when the inputs were applied independently. Okay, so to make more sense of this, go back to our example. So, like this one is U1, A1 sine omega 1t. This one is U2. So what if we make a combined input that's just the addition of these two? A1 sine omega 1t plus A2 sine omega 2t. What is the output going to be? Well, actually, I'm going to use the luxury of copy and paste here. The output is going to be the addition of these two. Maybe I'll clean that up a little bit. Y1 plus Y2. And it's easy as that. So think about this. Going back to the frequency response thing. We could run one test that combines many different frequencies at once. Like it could be U1, U2, U3, U4. Like it could be hundreds of frequencies. And I just combine all of those inputs into one combined super input. The output is going to be a combination of all of the individual outputs that would have resulted from each piece of each input. So you're going to get this output that's super rich in information, because this output is going to contain information about how the system responds to all of these different frequencies. Okay. So it's very cool, but there's a problem. There's a problem with this. Let me tell you what this problem is. So let's say that, because think about, for assignment 2, how do we determine the amplitude ratio and the phase for each input? It was dependent on, like, let's say this is the input and this is the output or something at that same frequency. You know, you could look at the time delay here and from here determine the phase. And you could like easily compare the amplitudes, right? And then you could determine the amplitude ratio. It's really straightforward if you just have two signals and they each have one frequency. When we combine a bunch of inputs, like this is what the data is going to look like. The input might look like, so this is input with lots of frequencies and amplitudes. So it's not even clear like which features belong to which frequencies, blah blah blah. And the output is going to look you know, just as crazy. So the question is like, so looking at these two crazy signals, how can I determine the amplitude ratio and phase angle for each frequency component? Because the advantage of running one test at a time is at least it's very clear how the amplitude ratio and the phase are related at a given frequency, because each test just gives you clean signals with a certain frequency. Okay, when everything's combined, now the problem becomes, how do I parse everything out? Okay, so here's the solution. And we owe this solution to our good friend Fourier. Well, I guess even before him, there was Bernoulli. I think Bernoulli was before him. Actually, I'm not sure. So, why do I bring up Fourier? Why do you think? Let's talk about what a Fourier series is. So, what our good friend Fourier said, and this goes back to superposition. It's kind of just saying the principle of superposition in a different way. It says any signal can be represented by a superposition of sinusoids at different frequencies. I want to show you a little example in Matlab. You've probably seen something like this before, but it's always fun to show again an illustration of how this principle works. So let's go over here. Let me show you what's going on here. I'm going to generate a sawtooth function. So it just looks like the edge of a saw. Let's look at this first. Okay. So it's very jagged. Each of these peaks is not symmetrical. It kind of like slopes differently on this side of the peak. Okay. What I want to do is show you that even this jagged signal can be very accurately represented by a superposition of many different sinusoids. And yeah, I want to show you this one. Okay, so the original signal is this sawtooth, right? And on top of this sawtooth, I have this red dotted line. It's kind of hard to see. But what this red dotted line is, this is the reconstruction of the signal using a bunch of sinusoids. So it's saying like, let's try to find a bunch of sinusoids that reproduce this original signal. And all of these are the sinusoids that we're adding together. So I can't remember how many I used in this code. It might be a couple hundred or something. But when you add all of these smooth... I know! It kind of... Because even this idea is very, very cool to me in 2021. I mean... and Fourier didn't even have all of the computational resources probably to make a figure like this. I guess you could sketch by hand and show the principle pretty nicely. But so this is how a Fourier series works. And I could use a very different signal and we could still break it apart. Like drawing these figures. But oh yeah, Bobby Ross would do it. What if we make a square? Let's run this. I think this will be... So look at this. Look at this. This is very beautiful to look at, by the way. But our original signal is this square. And you can find a combination of sinusoids at different frequencies and different amplitudes that reconstruct it almost perfectly. Even this like sharp edge. Yeah, this really is art. Like if you zoom in on these patterns here, it looks like some... How did Mr. Fourier come up with this? Yeah, wait, is this actually a textbook cover? Wait, what if we add these two together? I'm not sure what this looks like. Let's say y is y1 plus y2. I'm going to add the sawtooth to the square. And then we're going to decompose that into a bunch of sinusoids. So you add all those together. Remember, the red dotted line is when you add all these together. Yeah, trapezoid tooth. Like if you zoom in really close, you see that this red line still is sinusoidal. Like it's not perfectly straight. It's just if you zoom out. Okay. So let's go back over here. Let me find what I need. Okay, so what am I doing in this code? So let's say that the signal that we're trying to approximate is y of t. So it might have a weird shape, the trapezoid tooth, for example. So what a Fourier series tries to do, it solves a linear regression problem to fit that function with this. Summation from 1 to n of some amplitude times a sine at some frequency plus a different amplitude times a cosine at a different frequency. And it tests in different frequencies. Like it's going to get better and better the bigger that n is. So I think in that code I might have used like n equals 1000 or something. Oh, but you could rewrite this like a sine plus a cosine is the same as a sine with some phase angle. So, like in Matlab, when you take, like we've done a lot of linear fits in this class, right? You have some data points and you try to fit it with a line. So how does it find the best line? Well, what it does, so the line formula is y equals mx plus b. It tries to find m and b so that if you find the vertical distance between the line and every single point, and if you add up the square of each of those distances, we find M and B so that the sum of those square differences is the smallest. So that's a least squares problem, right? The Fourier series is exactly the same, except it doesn't use y equals mx plus b. It uses y equals this huge function, a1 sine omega 1 plus phi 1, 1 to n. So it's using way more parameters to fit this data. But it uses the same principle. It's minimizing the sum of square differences. So it's like a line of best fit, but it's a sinusoid of best fit. Many, many sinusoids. So what we can do is, let's go back to our problem, right? We're going to run a test where we're going to provide an input that's really rich in frequency content. And so the input is going to look like some crazy jagged line. The output's going to look the same. Well, what if we take this crazy input, we take that crazy output, and we fit it with this, a Fourier series? What is that going to give us? Effectively, that's going to take a complex signal and it's going to turn it into all of its individual components, which are smooth sinusoids of different frequency. And what if we do the same thing with the, so we have the input, what if we do the same thing with the output? So we're going to find sinusoids at the same frequency, right? Then we're basically going to be able to get the amplitude and phase by comparing these common frequency components in the input and the output. So it's a beautiful thing. You run an experiment that condenses a bunch of frequency information into one signal. You measure the output, and then you look at the resulting signals and you run a computational tool to break everything back into these individual sinusoidal components. And you can determine the magnitude and phase for each of these. So I'm going to finish with, I have more respect for Fourier now. Yeah, Fourier, and something that I like to remember too is that a lot of these abstract mathematical things that we learn in classes, they were derived by people to solve a problem. It's not, sometimes it's just for mathematical curiosity, but I would say more often it's to solve a serious problem of the day. And I think that even as I say that, I think the reason that they were coming up with this at the day, I mentioned Bernoulli earlier. They were studying the vibration of strings. It's like if you take this string and you pluck it, you know, it might vibrate like this. But they were looking at this problem and they were like, hey, I think that as a string vibrates, its shape is a superposition of a bunch of other shapes. You mean it just wasn't to flex on their intellectuals? I'm sure that was a big part of it as well. But I think Bernoulli and vibrating strings was, I don't know why they cared about this problem so much, maybe for musical purposes, but that was also related at this time. I want to show you, I'm going to post the Lab 3 procedure soon, but I want to show you a figure from it. Where'd you go? Getting closer, getting warmer. All right, we'll come back over here. So it's basically going to look like this, but I want to show you this figure. So, in this lab, the algorithm that we're going to use, we're going to do a Fourier series, right, to break down the signals. But we're going to use the fast Fourier transform. And I'm going to give you some code that expedites that process. But I want you to just remember conceptually that it's doing what we discussed today. So all of these, so you see there's like green dots as well as black dots in here. These black dots represent essentially a different frequency that was tested. Love the, yeah, I love these Bodhi plot, and it's for a real life system. So, we ran like, I think, basically you can do this with one test where you drive the beam kind of in a random fashion, and that random signal contains many, many different frequencies. And so each dot here represents one frequency that was embedded in that signal. And you're going to see that it makes these distinct shapes that resemble Bodhi plot shapes that you see in dynamic systems. So I know Mook likes to give those homeworks where he's like, hey, you know, what transfer function, can you figure out a transfer function that looks like this? Well, that's a real life thing. Because for the flexible beam, you're going to get a shape that looks like this. And if your goal is to get a model for that beam, well, you got to find a transfer function that has a Bodhi plot that looks like this. And so that'll be part of the lab report. We're doing a real life frequency response experiment. And I mean, you're going to do the same kind of thing. Like you can look at these plots for airplane wings, helicopter blades. People do this kind of stuff in industry so that when they look at their structure, they can find ways to maybe reduce the vibration. Like here, this peak is the resonant peak. And if I drive the beam at this frequency, it's going to vibrate a lot. So like in an engineering setting, you might be like, look, we need to reduce this peak by like 20 decibels or something. So you might have to design a damper that does that, or you can have an active controller that reduces this peak in practice. Or you could move this peak somewhere else by redesigning. So it's a very practical thing. But guys, that's it for today. Hope you enjoyed it. I think this is a fascinating topic that they build entire courses around, like modal analysis. So the higher the magnitude, the more vibration. Yes, that's exactly right. The higher the magnitude, if you have an input that coincides with that frequency, you're going to get a lot of vibration. Like, think of a helicopter blade, right? If it spins at, and we want to minimize it. Well, okay, think about it. I would say it depends if you want to minimize it. Like, okay, so if you're a structural engineer or you're designing a helicopter or an aircraft, and let's say this models the vibration of the structural vibrations of a wing. You want to make sure that if you have a peak like this, that during flight, you never encounter a condition where this frequency would be excited. It's okay to have peaks in your response as long as you never see those frequencies in practice. Otherwise, it could be catastrophic. sometimes you want this to happen. So a good example, so Dr. Karami at our university, a lot of his research is energy harvesting. And his goal is to build structures where they always encounter frequencies at this peak. So like a quick example, like if you have a flexible beam and you put some piezoelectric material on it, so basically as you deform the beam, it deforms this piezo, and the special thing about piezoelectric materials is that they produce current when you deform them. And think about it, like, what if you could store this on a battery? So when you build an energy harvesting structure, you want this thing to vibrate like crazy and deform this piezoelectric material as much as possible so that you store as much energy on this battery. So it's very interesting. Like, you could, for structural things, you want to avoid amplification. For energy harvesting tasks, you want to maximize, you want to exploit it so that you can get as much energy as possible. So yeah, like vibration, I'm curious what the last workshop's dealing with. Well, last workshop won't be vibration, actually. I think it's going to be, we're going to look at some digital filters to get rid of noise in a signal. But if you're interested in what we're talking about today, I think vibration and shock is a class you want to look into. I think we have 2 of those courses. There's like vibration and shock 1 and 2. And it's a lot about vibrations, frequency response. It's a cool topic. Well, guys, that's it for today. It's always a pleasure hanging out with you. I hope you're doing well. Hope you're hanging in there. We're getting close to the end. Peaceful Friday. Yeah. It does feel like a peaceful Friday, doesn't it? Not Prof. Hope you have a great weekend too. Not Prof is a calculus professor at UB. Say hi to Sandy. Hey, have a good one, Eric. HT test was over yesterday, so yeah, it does feel peaceful. Heat transfer. That guy's from WWE, right? Dude, WWE cracks me up. Love it. Vince. All right, guys, I gotta run to a Zoom meeting. So when you start in that RuneScape group, dude, I've been out of RuneScape for years. I wonder if my is my account still gonna be there? Oh my gosh. Okay, wait. Let me see. Do I even remember a password? Wait, I have to download it? Oh, come on. It used to just be in the web browser. I don't even think I can download it on this computer because it's a UB computer and I don't have admin access. Oh my gosh, this takes me back. Oh my gosh. We need a D&D group. Let's do it. The good old days of RuneScape after middle school. Oh my gosh. I was so addicted to that game in middle school. Okay, I got a Zoom meeting. I really got to run.